Today I am going to present experiment 5A semaphore implementation. In this presentation I will explain the aim, introduction to semaphore, real life example, function used, program execution in telnet server. The aim of this experiment is to demonstrate the utility of semaphore in synchronization and multi-threading. First of all, what is a semaphore? A semaphore is the synchronization mechanism used in operating systems. It controls access to shared resources when multi-threads are running. It allows only one thread to access the shared resources at a time and prevents race conditions. Let us understand this with a simple example. Imagine there is only one ATM machine. Two people want to use it at the same time. The first person starts using the ATM. The second person has to wait. Once the first person finishes, the second person gets access. A semaphore works in the same way by allowing only one thread to access the shared resources while the other thread waits. Now let us look at the important functions used in this program. The first function sem_init. This function is used to initialize the semaphores. And second function pthread_create. This function is used to create a new thread. And third sleep function. This function pauses the execution for a few seconds. And fourth function sem_post. This function releases the semaphores after the thread completes its work. And fifth function pthread_join. This function waits until all the threads finish their execution. And finally sem_destroy. This function destroys the semaphores and releases the allocated resources. These functions work together, synchronize the execution of multi-threads. Now let us understand the program step by step. First, the program includes the required header files. These libraries provide functions for input, output, thread creation, semaphore operations, and the sleep function. Next, a semaphore variable named mutex is declared. This semaphore is used to control access to the critical section. Then we define the thread function. The first statement, it checks whether the semaphore is available. If it is available, the thread enters the critical section. Otherwise, it waits until the semaphore becomes free. After entering, the thread prints the message entered. Then the sleep function pauses the thread for 4 seconds to simulate some work. After completing the work, it prints just exiting and executes sem_post &mutex to release the semaphores. This allows the next waiting thread to enter. In the main function, the semaphore is initialized with a value of 1 using sem_init function. This means only one thread can access the critical section at a time. Then, two threads are created using the function pthread_create. And next, the pthread_join function. This function waits until both threads finishes their execution. Finally, sem_destroyed function, it removes the semaphore and the program ends successfully. Now, let us see the execution of this program in telnet server. First, we create the source file using the command vi filename.c. In this program, the file name is sem.c and save the semaphore program. Next, we compile the program using the command gcc filename.c -lpthread. In this program, the file name was sem. So, the command is gcc sem.c -lpthread. This command compiles the program and links the POSIX thread libraries required for thread execution. After successfully compilation, we run the program using /a.out. In the output, we can see the message entered followed by just exiting. After the first thread completes its work and releases the semaphores, the second thread enters and displays the same messages. This output clearly shows that only one thread executes the critical section at a time. The second thread waits until the first thread finishes and releases the semaphores. Therefore, the semaphore successfully synchronizes the threads and prevents both threads from accessing the critical section simultaneously. So the semaphore makes sure that only one thread works at a time, preventing conflicts. With that, experiment 5A is completed successfully. Now, let us move on to experiment 5B, producer consumer problem using semaphores. In this experiment, we will understand how a producer and a consumer are synchronized using semaphores. In this presentation, I will explain the aim of this experiment, the producer-consumer concept, a real-life example, the semaphores used, the program, the execution and the output. Now we will see the aim of this experiment is to implement the producer to consumer problem using semaphores. In this problem, there are two processes called the producer and the consumer. First of all, what is a producer to consumer problem? The producer generates data and stores it in a shared buffer. The consumer retrieves the data from the same buffer. Since both processes access the same buffer, semaphores are used to synchronize them and prevent data conflicts. Let us understand this concept with a simple real life example. Imagine a restaurant, a chef prepares food and places it on the serving table. The customer collects the food from the same serving table. Here the chef acts as the producer, the serving table acts as the shared buffer, and the customer acts as the consumer. This is exactly how the producer to consumer problem works in an operating system. Now, this program uses three semaphores. The first semaphore is empty, which represents the available space in the shared buffer. The second semaphore is full, which represents the number of filled positions in the buffer. And the third semaphore is mutex, which provides mutual exclusive by allowing only one process to access the shared buffer at a time. Together, these semaphores ensure proper synchronization between the producer and the consumer. This is the producer to consumer program written in the C programming language. At the beginning, the required header files are included. Next, a shared buffer is declared to store the data produced by the producer. The program also declares three semaphores: empty, full, and mutex. The empty semaphore keeps track of the available space in the buffer. The full represents the number of items currently stored in a buffer. And final mutex ensures that only one thread can access the shared buffer at a time. The program contains two thread functions, producer and consumer. The producer function creates an item and stores it in the shared buffer. Before storing the item, it checks whether there is a free space using the empty semaphores and locks the buffer using mutex. Once the item is stored, it updates the full semaphores and releases the mutex. Next, similarly, the consumer function waits until an item becomes available by checking the full semaphores. It then locks the shared buffer, reads and removes the item, updates the empty semaphores, and finally releases the mutex. Finally, the main function initializes all three semaphores using the function sem_init. It creates the producer and consumer threads using pthread_create function and waits for both threads to complete using pthreads_join function and destroy the semaphores using sem_destroyed function. This completely execution of the program successfully. Now, let us see the execution and the output of the program. First, the program is saved as filename.c. Then, it is compiled using the command gcc filename.c -o filename -lp thread. After successfully compilation, the program is executed using the command dot slash file name dot. The output shows that the producer produces item 1 and the consumer consumes item 1. Similarly, items 2 and 3 are produced and consumed in sequence. This shows that the producer and consumer are properly synchronized using semaphores without any data conflict. Hence, the producer to consumer problem using semaphores is implemented successfully. We understood how semaphores are used for synchronization and how the telnet client and server communicate with each other. Thank you.